Hello to classes from across Canada. My name is Brent Beltala. I am the Executive Director of Partners in Research Canada, and I'm going to be your guest host for today. We are just going to get a couple of things organized here, and we will be get going in a minute. So our guest today is Rachael L'Orsa from the University of Calgary. I'm going to give Rachael a second to introduce herself in a minute. Right now, I'm just going to remind everybody to open your Q&A window. That's where you're going to submit questions throughout the presentation today. And we will get to those as we're able. And now I'd like to welcome Rachael to the presentation. I'll give you a second to introduce yourself, Rachael.
Great, thanks, Brent. So good morning or good afternoon, so depending on what province you're tuning in from right now. As Brent said, my name is Rachael and I'm a graduate student in electrical engineering. I'm part of a team that works on surgical robots, and my task in particular is to consider a situation where the robot and the surgeon that commands it are separated by a big distance, like being on the other side of the world from each other or even further apart. But Brent, did you have anything else you wanted to say before I launch into my full spiel?
No, why don't you get going, and if we need to interrupt, we will, but looking forward to your presentation. It looks like some interesting stuff behind you.
Yes. Okay, so just before I get into talking about my actual research, there are three other things that I wanted to address. And first off, this webcast is meant for students in grades 5 to 12, which you probably already know, and that's a pretty broad range of ages. So I'm going to try to keep things as easily understandable as possible, but include some more advanced stuff as well. And if you want to see a more basic introduction to what our lab does, then please check out the Partners in Research YouTube channel and watch the K-7 robotics presentation I did in February 2017. So I'm just going to share my screen here, so you can see my presentation. Okay, so I'm talking about smart surgical robots in space. And I want to make sure that everybody understands two basic types of robots. There's teleoperated robots and there's autonomous robots. This is a great video from the Institute of Robotics and Industrial Computing in Spain, which shows what teleoperation looks like. Teleoperated robots are controlled from afar. And another way of saying this is remote controlled. So this means that someone is watching the robot to make sure it does the right thing and can adjust their commands if changes are needed. Okay, so here we can see the two different types, teleoperated and autonomous. So in contrast, autonomous robots are given a complete set of commands before they start their task and have to be able to figure out which command to run at what time, depending on what's happening in their environment. In reality, there are robots that cover the whole range from remote control to autonomy, and many can be run in both modes. So the third thing that I want to talk about before getting into my research is the Lunar Gateway. It's a really exciting international project where the goal is to put a new spaceship, which you can see here, out orbiting the moon. And Canada is providing the robotics. So I know this slide is pretty busy, but hopefully you can see right there, that's us, that's Canada, and we're responsible for the robot arm. So the Gateway is going to be quite different from the International Space Station, or the ISS, for a number of reasons. For starters, it's going to be smaller than the ISS and might only have astronauts on it for a few months per year instead of year-round. It's going to serve as a home base for moon exploration, a testing ground for robot autonomy, and maybe even a launch pad for missions to Mars or beyond. But when it comes to astronauts, oh no. Okay, well, when it comes to astronauts, sorry, you'll just have to bear with my, my blank screen there for a second. There's a big difference for this new spaceship, and that's that while the International Space Station is only 400 kilometers away, the gateway is going to be about 400,000 kilometers away. So our astronauts are going to be a lot further from home, and if they get sick or hurt, it's going to take them about 5 days to get from the gateway to an emergency room. So they're going to have to be able to fix or at least stabilize any dangerous medical conditions on their own. And the Canadian Space Agency, or CSA, actually has a great statement about this from former astronaut Bob Thirsk, and they've given me permission to share it with you today. So I'm going to see if I can get that working. Okay.
Is that humanity will soon be leaving low Earth orbit and heading further into the solar system and into deep space. My experience has taught me that whenever we venture to a different place in space, or when we take on a different activity that we've done before, we can expect a new healthcare concern or another medical problem to arise. As we leave low Earth orbit and venture on to these deeper space destinations, we must create medical care systems that make the astronauts more autonomous for delivering their own care. I expect that robots and artificial intelligence will play a major role aboard these long distance and long duration space missions to help astronauts with the diagnosis and treatment of maladies that might arise.
Okay. So you might have noticed this guy here in Bob's video. And that's Dr. Garnet Sutherland, who's a top neurosurgeon who figured that robots might be able to help perform surgeries better. And he built a team that built just such a robot, and it's called Neuroarm for its ties to the company that built Canadarm 1 and 2 robots. So I work in Project Neuroarm's Surgical Performance Lab, where we focus on improving teleoperated surgery, or telesurgery for short. So a couple of years ago, we started thinking about whether or not we could teleoperate a surgical robot on a spacecraft from Earth. In this scenario, a surgeon would send commands to the robot through the same Earth-space communication networks that let us talk to astronauts on the ISS, and the robot would have to follow those commands. But it turns out that there are some serious challenges to overcome if we ever want to get this idea to work, and they come from this Earth-space communication network. The main ones are time delay and bandwidth restrictions, and I'm going to talk to you about those now. So imagine that you're driving a remote control car, but you can only see where it's going through a camera that's mounted on the car itself. Let's say there's an obstacle in front of the car, and there's also a 10-second round trip delay between when you send your command and when you get updated images from the camera. In this scenario, not only will you not see images of the obstacle until about 5 seconds after the car has hit it, but your go forward command is still going to be sent to the car for another 5 seconds after you stop sending it. So clearly this is not good for something like surgery, where you absolutely don't want to hit anything accidentally. So the next challenge has to do with how much information you can send through an Earth space communication network at a time. This is called bandwidth, and you can kind of think of it as something like a hallway. So if one person is walking down a hallway, that's fine. They can do cartwheels, they can run, they can do whatever they want. But the more people you have trying to walk down that hallway at the same time, the more it gets clogged. And eventually you're going to find that there's some maximum number of people that can fit through the hallway at the same time, and that's kind of like bandwidth. So surgeons need to see what they're operating on, which means they need high quality video. And video takes up a lot of bandwidth, maybe more than Earth space communication networks can offer. So trying to transmit high quality video through these networks might be kind of like trying to fit a watermelon through a straw. It's just not going to work, at least not with technology in the state that it's at right now. So at this point, we started thinking, maybe we can't teleoperate a surgical robot in space. Maybe it needs to be somewhat autonomous. So the next question is, how do we make a robot smart enough to do surgery on its own? And this is actually my research. So a promising solution might be something called a neural network, which falls into the category of artificial intelligence, or AI, and it kind of works like a coffee filter. So when you make coffee, you put coffee grounds and hot water through the filter and get your coffee out the other end. Neural networks work similarly because you can put building blocks inside of them, or feed them building blocks, and then build them or train them to only let the things you want through to the other side. So in our surgical robot scenario, we might have sensor information as our input, and then train the neural network to detect events such as contact between the robot's tool and the patient, and then use that information to slow or stop the robot, or maybe start another set of instructions. So this cycle of sense, interpret, and act is the framework for robot autonomy. Sensors are really important for this cycle because they allow a robot to see, hear, feel, and more. Thus, it's really important for us to choose sensors that will help our robot make good decisions. This picture you can see right now is from some experiments that my friend Lynn and I recently did. We were testing out optical fibers, which are kind of like what you see in those fake Christmas trees that have the LEDs and they change colors. They cycle through a bunch of colors one at a time. And these optical fibers, we wanted to examine their potential for use in robot surgery. So we put one of these glass fibers inside the tip of a needle and then poked some pork ribs from the butcher shop with it. And we shone light through the fiber while we were doing this, and then measured how much of it got reflected back. And as you can see here, we found that the light changed enough for us to recognize important events like touching the meat or puncturing through different layers that are within the meat. And the thing is, this is really exciting, but it's just the first step, because we can look at this plot as human beings and say, oh, okay, this increased reflectance right here means that we're close to the patient. But we need to teach robots how to recognize that too. So the next step is to put this sensor information into a neural network like the one you see here, which can quickly memorize what different combinations of inputs mean by doing some math. And you don't need to understand the math to get this part. It's just enough to understand that neural networks work by filtering some input information through a mathematical structure. And it's really, in a lot of cases, it's an actual structure like you see here. So now that you've had an introduction to surgical robotics for space, you might be wondering where you can learn more or how you can get into robotics or AI. And luckily, Canada has a lot of youth robotics competitions. There's VEX, there's RoboRave, and 4 different levels of first that actually cover from like 6-year-olds up to grade 12. Sorry, I've got a now robot talking in the background here. So you can also find a ton of information and tutorials ranging from beginner to advanced on websites like YouTube and Instructables. There unfortunately isn't a lot of youth-specific instruction available for AI yet, but you can find a lot of free adult-centric training on websites like Coursera. And you can also check out AI for Youth, which is a really forward-thinking Canadian not-for-profit that was started by high school students who think that today's youth need access to tomorrow's AI skills now. So if none of these things are available in your area, you can also try to find a mentor or a makerspace to help you learn how to program, how to design, how to build, and how to problem solve. I'm gonna stop my my slideshow for a minute so that you can see the makerspace that I'm in right now at the Schulich School of Engineering. Makerspaces are an awesome learning resource. Hopefully you have one at your school or you have one in your town. They're kind of like a library full of tools. Often they'll have 3D printers and stuff like that. So some makerspaces, like the one that I'm in, actually have a lot of robotics resources as well. So it's a great way to start learning about robots. You can kind of see in the background there, we've got a Now robot who seems to be quite restless. He doesn't want to stop moving. And we've got a Vex Robotics Clawbot in the back, and we've got a number of other resources that are a little more advanced than these and going all the way up to super duper advanced. So if you can get yourself into a makerspace, then that's a great way to start learning about these things. And I think the one thing that I can say for sure is that if you're interested in robotics and AI, you should start planning to study STEM. And by STEM, I mean science, technology, engineering, and math. It might be the right fit for you. Please send me your questions.
So thank you very much, Rachel. Hopefully we get some questions popping into the Q&A right now, and I'll get to those in a second, but I had a couple of my own as well.
Sure.
One of the image that you showed right at the start of your presentation with the woman moving and the robot mimicking her movements, how many sensors is required in order to do something like that?
Well, it depends on how many things you want to move. So normally in robotics, you could say that we would call a single joint a degree of freedom. So I have 1, 2, 3 degrees of freedom just in a single finger. So if you wanted to control all 3 degrees of freedom in that robot finger, for example, you would need to have sensors that tell the robot what each of those joints is doing. So, I mean, there are tricky ways of getting around that and trying to kind of assume what other degrees of freedom are doing, even if you don't have a sensor on them. But in general, you would need a sensor for each joint that you want to control.
Fabulous. Some questions from Lee Krantz's class. First of all, a question about finding a mentor for schools, specifically in Toronto. Maybe you can, in generality, how would you recommend somebody find a mentor in robotics?
Well, I guess in a city like Toronto, I mean, I don't have much familiarity with that area, but I would expect that there's a lot of industry, and I mean, there's a fantastic university there, the U of T, and there must be makerspaces. So one of the best ways to find a mentor would be to look for companies that do this kind of thing, companies that work in robotics, such as McDonald Detweiler and Associates, the company that built the Canadarm. I know they're in Ontario. I'm not sure if they have offices in Toronto. Look for any companies that do this kind of stuff, and even try cold emailing them to say like, hey, I'm a student, I'm interested in this. It's pretty hard for professionals who like what they do to turn down a student who wants to learn more about it. Similarly, Ontario has tons of FIRST robotics teams. And even if you don't want to join a competitive team, they're fantastic resources because they know all about the robotics community. So you can go to them and say, hey, I really want to find a mentor who can teach me this. And I mean, they might try to recruit you for their team, but they'll be really happy just to connect you with people who want to share their passion for robotics with you. And also any universities or colleges that offer programs like this, you're going to find university or college level students who are excited about it too and know a little bit more than you and would be happy to share what they've learned.
And I'll recommend to the teachers in the classrooms today, if you do go to the Partners in Research website and look at Expert Book and search for robotics, you will find not only Rachel, but other robotics experts who have volunteered their time to participate in our program. So that's a good source as well. Another question from that classroom was about other robot applications that biology might use.
Ooh, biology. That's a good question. It's a little bit further from what I'm used to thinking about. So I certainly can't tell you the widest range of what's out there. Let me see. Well, in a lot of cases, robots are used to do things that we don't want to do or that are too dangerous for us. So for example, if you needed some reagents for an experiment in biology that were maybe too strong for humans to be around, you don't want to risk being in contact with them, you could assign that task to a robot and have the robot precisely mix your ingredients for you. There are, I guess a 3D printer is not a very good example of this, but I know that in bioengineering, they're working on 3D printers that are actually printing out cells. And I mean, there's kind of an ongoing argument about what qualifies as a robot and what doesn't qualify as a robot, but a 3D printer is technically a smart machine that can follow commands mostly autonomously. Sometimes they get all spooled up and problems arise and they can't fix that themselves, but you know, 3D printing of cells into a, you know, like the matrix of a nose, so you could grow a prosthetic nose out of real cells for someone, that might also qualify as robotics in biology.
Excellent. This is a question that I don't know that I could have come up with, but is it possible for the autonomous robots to change their own code?
Oh, that's a fantastic question. And it's actually a really hot topic of research. So let me see. So if you think of that neural network image that I showed you, where it had all those kind of peaks in it that were overlapping, there are some algorithms where it can choose where the peaks need to be and how wide they need to be in order to get the best performance out of your robot, which is, you know, recognize the thing you need to recognize or do the movement that you need to do. So in that sense, they are actually self-learning. I can't speak to the cutting edge in terms of what programmers are doing. I know that they're definitely looking at code that can recode itself or change itself. I'm not sure how much of this has actually been implemented in robotics, but it's kind of the plan for the future. We do want to have robots that are resilient enough to environments that they can manage difficult situations. And in order to do that, we can't possibly teach them every single possible thing that can happen. So they need to be able to kind of change their own responses to things.
Very interesting. A couple of, sorry, a question here about back to the work in space. So how would you guarantee that the surgical sensors are working, and what happens if they stop responding? And then along with that, how trained can astronauts be to facilitate this process?
So astronauts are extremely good at following instructions. Obviously, these people are the top of the top, the best of the best. They're really, really smart, really capable people. And in a lot of cases, they have multiple backgrounds. Maybe they're an engineer and a medical doctor, or an engineer and a fighter pilot, or whatever it may be. So they're very good at following commands. And there's kind of an ongoing debate actually amongst our surgeon collaborators here at the University of Calgary over whether or not it would be best to try to telementor another astronaut through a life-saving procedure, or actually build a robot to do it. And this is kind of an open question of debate because we don't know the answer. We do know, take for example, chest tube insertion. So if you get hit in the chest and you start building up air or blood between your chest wall and your lung, it can cause a really dangerous situation where the pressure becomes too big and it collapses your lung and you can no longer breathe. This is bad, obviously. So what doctors do when you go into the emergency room is they basically put a little tube in there in that space, and then they empty out, they drain out all of that fluid or air. And as it turns out, actually recent research here has shown that trauma surgeons are really, really good at putting these tubes in, but residents and emergency department docs or other people who don't get a lot of experience with it, or they're not doing 8 of them a day, they actually have like a 40% complication rate. And not all of those complications are putting it in, but sometimes that means actually putting it into the wrong place and stabbing something you're not supposed to stab. So we suspect that it's theoretically you could have an astronaut do this procedure, but if they don't know what to feel for, they might push too hard and end up accidentally puncturing their co-worker's lung or their heart or something like that. So you're absolutely right. Obviously, we would need to put fail-safes in for a robot to do it. The idea is that a robot can operate a lot faster than we can. So when you talk to surgeons about this procedure, they say, oh, I just push until I feel a pop. And that's how I know I'm in the right place, which literally they've been doing it this way for as long as they've been doing chest tubes. And it's very successful for people who are good at it because they know what it feels like. But it's really hard to, to measure that, a difference in feeling on like a tiny scale. So robots actually can, because your sensor can be very, very sensitive, and you can check that sensor, once every millisecond, and they can react to it a lot faster than we can. So theoretically, a robot should be able to recognize, oh, I punctured, I'm not going to move anymore. But in order to do that, so what happens if the sensor fails? You need multiple sensors. You need like double of everything. Basically, redundancy is a big thing. So you're not just going to rely on one sensor. You might have two of the same sensor, and then you might have two different types of sensors that can help make sure you're not going to have a failure. And if you do have a failure, the system stops moving, and an astronaut would have to take over, like another astronaut who is helping.
I love the chest tube example. It reminds me back of my days working in intensive care, and I watched lots of chest tubes go in, and it is an art, not a science. It's really different. So that's a great example. I'm going to combine a couple of questions here. How long have you been in school to get your position, and how long is it taking you to do what you do now?
So actually, I'm going to share my screen for a second, because I actually have a slide on grad students, because a lot of adults don't even know what grad students are. So let me go over here. Okay, so grad school. It's very similar to grade school. In grade school, you have elementary, which, I mean, these numbers are based on my hometown. We had kindergarten to grade 6, then we had a middle school, which was 7 to 8, and a high school, which was 9 to 12. So university is very similar to that. When you first go, you do a bachelor's degree, which might be 4 or 5 years, depending on if you get work experience at the same time or if you change your mind about what you want to do. And that's kind of like a basic introduction to a broad range of things. So if you want to study more about one single thing, you do a master's degree, which is kind of like it's kind of like a multi-year science fair project in a sense, because you kind of have like a dedicated project that you're working on and you're trying to figure something out. When you decide that you want to be an expert on something, you get a PhD degree or a Doctor of Philosophy, and that could be anywhere from 3 to, actually, I have a friend who took 10 years at Stanford on his PhD degree, so I hope not to take 10 years, but some people, that's what it takes. So anything beyond a bachelor's degree is called, we're called graduate students. So if you do the math from what's on the screen, I have been in school for a while. And I don't want to scare you guys off with the number of years I've actually been in school, because I did a few more degrees than I needed to, just because I really was enjoying myself. I did mechanical engineering at first as a bachelor's, and then I also did a bachelor's of French and Spanish with a minor in computer science. And surprisingly, computer science is a lot of languages, so it's pretty much just a degree in languages. Then I did a master's in electrical engineering, and now I'm in a PhD of electrical engineering. So I think it's been about 13 years. But I took my time. I was firefighting on the side and doing a bunch of other fun things. So I did not take like a straight line progression through that career path. So I would say that to work on the stuff that we're doing right now, we have master's students in our lab. We also have undergraduate students who serve as like summer students and interns. So basically, as long as you're in a relevant program, like we pretty much only take computer scientists and engineers in our laboratory, and some health sciences professionals. So as long as you're in something relevant, you can theoretically get into a laboratory that's doing some really cool stuff.
Very cool. So we're going to get back to some more interesting robotics questions specifically. So Devin and Angus is asking if robots will ever have emotions.
Oh, yes. Okay, so I actually have friends who are working on this to an extent right now. So there are groups that are able to program what looks like an emotion into a robot, but we don't actually know how emotions work in human beings. We know that we feel them. We know that there's some neurotransmitters involved, but and there's triggers. But I mean, it's not my background, so I can't really tell you about how much information and how much work has been done out there on this. But we're at the point where we have software that can recognize emotion in humans. And so they're starting to give robots the ability to say, oh, I can see that you're angry with me, so I'm going to change my behavior according to that. Whether or not we can actually transfer that behavior, that emotional behavior, over to a robot kind of remains to be seen. Although my PhD supervisor, so I already showed you the photo of Dr. Garnett Sutherland, the neurosurgeon. I've also got an engineering supervisor, and her name is Dr. Chris McNabb. She's working on giving personalities to robots, and that's kind of, she's looking at, can you change, like say you're not a risk taker. There's kind of like a personality around being an introverted, non-risk taking type of personality, and she can translate that into how the robot responds to what it perceives as risks. So it'll avoid the risk as much as possible. So it's not quite the same thing as programming emotion into a robot, but I'm sure if we can figure out how it works in humans, we will definitely put it into robots. And even if we can't, I'm sure we'll try mimicking it in robots.
Very cool. We are over time, but there's a lot of questions, so hopefully you've got a couple of minutes to answer a few more. We had a question asking where a junior to intermediate level students, grades 6, 7, and 8, might start with a robot. What is the best robot to start with?
Ooh, that's actually kind of a tough question because there are a lot of different educational robotics platforms out there. I think I would have to go with Lego Mindstorms, partly because they're so prevalent in a lot of schools. Like a lot of schools have them kicking around in some dusty back corner, and nobody's using them because a lot of the educators don't know how to use them. They've never been trained on it, and they don't have the time to learn how to do it themselves. So if your school happens to have Lego Mindstorms, they are a fantastic place to start. They're kind of one of those platforms where you have components that are pre-made for you, but you also can customize things in terms of your building. Sorry, we've got some students trying to get into the makerspace right now. Yeah, so I would definitely recommend the Lego Mindstorms. I know that they've just released a new one, the Spike Prime, and it looks amazing because they've really upgraded all of their sensors and whatnot, even though they put it in like flashy colors, so you might think that it's less serious than like the EV3, but it's actually a really, really nice platform.
Very cool. So I'll try and ask one more question that encompasses a number of questions that are in the Q&A, and it's really around safety precautions around the space robotic surgery. What are the things that you can put in place, stop gaps, backup systems, etc., that ensure the safety of those procedures?
Honestly, that's a pretty complicated question to answer, and it's not really, I don't have a ton of expertise on that because I'm more focused on how do we program the robot to do what it needs to do. But in general, you would have different kinds of controls. So you would have administrative controls in terms of how the astronauts are allowed to use the robot. So it probably is always going to have another astronaut watching, and they know what is safe and what is not, and they, you know, they've got their finger on the emergency stop and they're ready to stop it if they see anything that's out of line. You'll probably have what you might call like engineering controls, where the hardware, like the actual pieces of equipment themselves, are designed to minimize the risk. So for example, say you're doing a chest tube insertion and you happen to have an ultrasound, because for example, they have ultrasound on the ISS for experiments and whatnot. So you do an ultrasound of your patient and you get an idea of how thick their chest wall is. Then you can put something on your needle that says that it's gonna like physically stop it from entering too far past that point. So if your chest wall's, you know, 3 centimeters, maybe you put the stopper at 3.2 centimeters, so it cannot go any further. And then the last way to do it would be in the programming, so that you've got multiple checks and balances in the programming, like multiple, we call them, you know, safety watchdogs. So programs that are running kind of outside of everything else and that are constantly saying, is this safe? Is this safe? Is this safe? So you have 3 different levels in general of safety that you would add on to this.
Excellent. Thank you so much. So we have a bunch of questions that we're not going to be able to get to. If it's okay, maybe I can forward you a couple of those questions, Rachel, and we can put those with the recording.
Yes, absolutely. I mean, I have a little bit more time today if everybody else has time, but if not, I'm more than happy to answer your questions through email.
Fabulous. Well, if you've got a couple of minutes, then we'll ask a couple of more.
Sure.
Classrooms, if you need to drop off, we understand, and we will get some of these questions done text-based following. There's an interesting question here asking about nanorobot surgery.
Oh, okay. So I haven't seen a lot in terms of like a nanoscale, but actually last summer I had the privilege of spending some time at one of the Max Planck Institutes in Stuttgart, Germany. And they had a group that was working on microscale robots, and they were really cool. So they'd actually made these, I don't know if you can technically call the equipment itself a robot, because it was basically just like a screw. It was basically like a tiny, tiny little screw. And they were able to steer it through the human body using either magnets or ultrasound waves to push it. And the idea for this robot is that they would push it through arteries up to where there was a blockage. And then they were able to control it to kind of start actually drilling out the blockages. So that's kind of the extent of what I've personally seen for really small scale robots, but I know that there are quite a few research groups that are working on that. It's super promising.
Back to some surgical questions. This is an interesting one about viruses. Can viruses impact a robot?
Yes. And some fun research has been done where researchers have hacked their own systems or other researchers' systems. So for an example, I believe there was I can't remember, I think there were an Australian group that had hacked some 3D printers that were making drones, so that there was actually a flaw in the structure of the drone, and they were able to activate that and break the drone. And so that's not so much a virus that would get into the drone software and affect it, but this is a really good point, because there's a lot of, I mean, you see it in the news all the time. We're talking about, you know, smart everything. So if you've heard of the Internet of Things, and people are talking about smart homes where you've got your Nest devices and everything's connected. Well, the way they're connected is through a network. And as soon as they're connected through a network, if someone gets access to that network, then they can theoretically gain access to all of those devices that are in your home. And it's no different in an operating theater too. Obviously, hospitals take great care to make sure that patient data is protected. But if someone wanted to or was able to hack into a hospital system, theoretically, they could potentially take control of the robot. So cybersecurity isn't a focus of my research, but I know that there are ton of people working on this and trying to create the preventative measures in advance so that this doesn't become an issue, but it's definitely a consideration when we're building robots.
That's great. Two other questions that I really wanted to get to. And this one, again, this goes back to my time working in the ICU. Question from, I think is Mr. Bates' class. Can your robots perform CPR?
Well, do you mean on Earth or in space? Because actually CPR in space is really hard. I've read some research where they actually did trials where if you've ever done a CPR course on one of those dummies, so they had that in a spacecraft, and they found that they actually had to put their hands against, I shouldn't call it the ceiling because there's not really a ceiling and a floor, but they had to put their hands against one end of the spacecraft and then, or like brace their feet and then try to use their whole body to do the CPR because it actually takes a lot of energy. I'm also a paramedic, by the way. That's part of why it took me so long to go through school. And I can tell you firsthand that CPR is very, very energy intensive. It takes a lot of energy. So I have not come across a robot that has been designed to do that. But I feel like in comparison to some of the things that we're designing robots to do, that would be a fairly straightforward design, in the sense that as long as you can design a robot that's safe to interact with humans. So if you've heard about cobots, which stands for collaborative robots, these are robots that are super lightweight and they've got springiness in them instead of being those really tough, rigid, industrial style robots that you see throwing around cars in assembly lines. We make them springy on purpose so that if they hit a person, they're not going to hurt the person, they're not going to hurt themselves, they're not going to hurt any equipment they knock down, something like that. So if you designed a cobot that was safe to be around humans and knew how to recognize A, that CPR was needed, and B, where and how to do it properly, then yeah, you could definitely have a robot do CPR.
So we'll finish on this question because I think it's a good segue from your last answer about interaction with humans. Mr. Oreo's class asking about ethical issues that may arise from using robots to carry out a surgery.
Yeah, that's a really good question as well. And it's not just ethical considerations. I mean, obviously that's a very chief one in all of our minds, but the legal implications as well are probably going to be a problem, and new policies will have to be made to address this. In the early 2000s, there was a transatlantic operation where there was a patient in France and a surgeon in the States, and they removed the patient's gallbladder via a teleoperated robot. Everything went on without a hitch, and it was great. But the reality is, if something had gone wrong, who is responsible for that complication? So unfortunately, the surgeon who did it, who may or may not have been at fault for the mistake, can't even help the patient now. So now there are expectations that the staff that are right beside the patient have to handle this new emergency and deal with the complication. So it becomes this really complex system of, is it a mistake? What is the mistake? What caused it? Is someone at fault? Could it have been prevented? How do we fix it? Who fixes it? Who's responsible for it? And I feel fortunate that I can kind of mull over these questions in the back of my mind, but I'm not involved with the policymakers who are going to have to write some firm regulations on that. So as these robots emerge, we will see governments taking a stance on these types of things.
Fabulous. Thank you so much. Rachel, thank you for your time today. It's been a very interesting presentation.
Thank you very much for having me.
And to the classrooms, to the teachers that are still with us, and anybody who's watching the recording, just to let you know, a good segue from today's session, talking a lot about robots in space, Partners in Research, and the Center for Planetary Space and Exploration at Western University, in conjunction with the Canadian Space Agency, are starting promotion of the Junior Astronaut Program. So you will be seeing webinars coming up in the next couple of weeks. presented by Partners in Research, talking about how to get involved at the Junior Astronaut Program. So I hope classrooms, teachers will all take the opportunity to be involved in that. Thank you again, Rachel, and thank you to the classrooms for being with us today. Have a good day. Take care. Bye-bye.